right, in this video, we're going to walk through the solutions to some practice problems. So we're going to look at practice problem 4, which is going to be calculating different types of concentration given a pile of information that we have. So we're going to try to calculate molarity, molality, mole fraction, mass, volume, percent, and parts per million. And we know the mass of our solute, which is going to be potassium chloride. And we have a volume of water and a volume of the total solution. And we know the density of the water and the density of the solution. And they're different, but similar because the water is just the water, but the solution is the water plus the potassium chloride. And so its density is going to increase a bit. So we'll use all of this to go ahead and calculate these. Let's start with molarity. All right, so for molarity, we're going to need to have moles of our KCl on the top of our fraction, and then the volume of our solution on the bottom. We're going to want that in units of liters. So we have that volume of solution, right? We have that 1.002 liters. So that's done. That's fantastic. So this right here is that 1.002 liters. So we really need to calculate those moles of potassium chloride. So this is a mass to mole calculation. So I'm going to take my 3.75 grams that I'm told my potassium chloride solute is going to weigh, and I'll convert it using its molar mass that I determined from the periodic table. And so that'll be 1 mole will weigh 74.55 grams. And that's the molar mass of potassium chloride. And that'll give me 0.0503 moles of KCl. Great. So now I can input that number, that value, up here. So when I calculate my molarity for this solution, it's going to be that number of moles that I just calculated, my 0.0503, divided by my volume of my solution, which is 1.002 liters. So my molarity is going to equal 0.0502 molar. All right, so that's molarity. And this is one that we use in the lab a lot. So hopefully this one comes pretty easily. And it really relies on some of those calculations that we used in stoichiometry a lot, like mass to moles or moles to mass. All right, now let's do molality. I'll do it over here. So remember, molality is going to equal our moles of potassium chloride. And now it's going to be divided by the mass of our solvent at the temperature that we're working at, which we're going to assume, since it's not given, is room temperature. So it's going to be the mass of our water. So in this case, we've got the moles of potassium chloride already. We calculated that to be 0.0503 moles. So I need to get this mass of water. I'm going to want it in kilograms too. So in this case, I've actually been told the water's volume that's added to the mass of KCl. So that kind of makes things a little easier. If you don't know the actual volume of water, but you just know the volume of the solution, you can always find the mass of the solution if you know its density and subtract the mass of your solute. That'll give you the mass of the water just on its own. But we have 1.00 liters. So I'm going to use my density of water to then convert into the mass of water that I have, and I'll convert that into kilograms as well. So my density of water units are in grams per milliliter. I can either convert that into kilograms per liter, which is probably the more straightforward way. But if that doesn't come to mind, I'll show you the slightly longer dimensional analysis method. I'll convert this to milliliters. And then I'll use my density to convert volume into mass. So that'll be times 0.998 milliliters per, or sorry, grams per milliliter. And then I'll convert this into kilograms. And doing so, I'm going to get a mass that is 0.998 kilograms of just water, right? So that's just my solvent. So that molality which is like the little m, right, is going to be equal to my 0.0503 moles divided by my 0.998 kilograms of water. And that's going to go ahead and give me a value that is 0.0504 molality. So you can see it's really similar to molarity, but it's slightly different. Actually, let's do this. Yeah. Okay, next we have mole fraction of solute, mass per volume, and then parts per million to go through. So let's start with our mole fraction. So our mole fraction of our solute, so for our KCl, is going to be equal to the moles of our KCl divided by the moles of our total solution. So it'll be the moles of KCl plus the moles of water. So I know the moles of KCl already, right? We've already calculated that. It's that 0.0503. So I really need to figure out the moles of water. Well, I know the mass of water, right? I finally figured that out. Yay. So I'm going to go ahead and take that mass of water and use its molar mass to convert it into moles. So for this one, I have 0.998 kilograms of water. I'm going to convert that into grams so I can use grams per mole for my molar mass. And then I'll convert into moles using 1 mole is equal to 18-ish grams from the periodic table for water, H2O. And that will give me a value that is 55.44 moles of water. So I'll be able to plug that in. So that mole fraction of potassium chloride will be equal to our 0.0503 moles divided by 0.0503 moles plus 55.44 moles of water. That water really dominates the denominator of this fraction. And calculating that and plugging it in, I'm going to get a value that is small. It's 0.000906. And since my units cancel, this is just a fraction without units, right? So I could also write this as 9.06 times 10 to the negative fourth as well. And that is my mole fraction. Let's move on. Let's try mass per volume. So this is going to be equal to the mass of my KCl divided by the volume of my solution times 100%. And I already know these things, which is great. I know that my KCl mass is 3.75 grams. I know my volume of my solution is 1.002 liters. Now, for this one, we want to make sure that our volume of solution is in milliliters rather than liters that we used with molarity. So I'll make sure that I convert that into milliliters when I perform this calculation. So this is going to be equal to, my 3.75 grams of my KCl divided by my 1.002 liters and then converted into milliliters. So times 1,000 milliliters divided by 1 liter there on the bottom times 100%. If you have a percent button in your calculator, don't use it. Typically that actually changes things around, but times 100, I guess I should say. And that's going to give me a value of 0.037%. And so that's going to be my mass per volume. All right, one last one. We are going to do parts per million. So our parts per million is super similar. And we can do this based on mass, or we can do this based on volume. Since we have the masses of our solution and our, or we have an easy way to get to the total mass of our solution. We have our mass of KCl already. Let's do mass rather than volume because we don't have a density for potassium chloride. So it'll be the mass of our potassium chloride divided by the mass of the total solution. And parts per million means it'll be times 10 to the sixth. So we know that that mass of potassium chloride, that's 3.75. So we need to figure out this mass of solution. So I know that I have a 1.002 liter solution. I could use its density that's given to me to figure out this mass. So I'm going to convert this into milliliters since my density units are in grams per milliliter. So times 1,000 milliliters divided by 1 liter. And then multiplying this by 1.05 grams divided by 1 milliliter for the density of the solution rather than the density of the water. Let me double check that. Yep, 1.05. Uh, and that'll give me grams, which will be perfect. So that equals 105, 2.1 grams. So I'll use that. So my parts per million is going to be equal to 3.75 grams divided by 1,052.1 grams times 10 to the sixth. And that gives me a value of 3,676 parts per million.